like same shit. Put up the end. Where's the camera?
The camera's here.
Mind recorded was talking. You can read the board, perfect.
Right. Has anyone not had a chance to read the feedback notes that I gave? You haven't?
No.
Right. You should all have a paper copy of it now. And you should see that I've tried to make something of the graphs of the results that you created. I haven't included the results. I'm assuming you've all got them. Particularly the group that we had last Tuesday. I've suggested you've got to be very careful with the results that you saved. Because there's a calculation embedded in the PowerPoint, then you've got to be a little bit careful. I've asked you to check that calculation. What I discovered though, between the two sessions, the voltages which were displayed on the computer screen got switched round. So whereas we thought the first one was the voltage being applied to the servo valve, and the second one was the voltage coming out of the tacker generator, they were actually the other way around. Which meant that you got graphs that didn't look like graphs that we were expecting. But PowerPoint being so clever, if you just swap columns, as I think they did before they saved them, it sort of moves the formula to where the column has now gone. So you end up with calculations that you trust, but you shouldn't. So that was the first thing to remind you of. I'll remind you again, there is a coursework element attached to on the end of that. And I'm hoping that when I see you again in 2 weeks' time, you will have all handed them in, and so I can pick them up that day. I'm due to see you in 2 weeks' time. Dr. Hoolan is next week. He will see you in the third and the fourth weeks. And then the last week of term, I think I'm down to see you again. So I've got today's session, and because we rushed through chapters 3 on pumps and motors, and chapter 4 on valves, really to cover the bits of those that were embedded into the lab work, which we'll look at now, that's what I want to do today. So first thing, I want to run through the lab to make sure you understand it. And that, I hope, will be helpful because you're asked to identify the components of the circuit diagram in the lab sheet. And I've told you half of one of my questions is a similar exercise, asking you to identify and describe components in a circuit. There's usually at least another part of a question based on the lab. So of the two questions, there are 4 questions on the paper, 2 from Dr. Hoolan, 2 from me. Part of one of my questions is also to do with the lab. So if you understand the lab, A, you should get a good mark for writing it up, which counts towards 30% of the module. And B, you should be prepared for a reasonable choice when it comes to the exam paper. So by going over chapter 3 again today, and chapter 4, there are some things which we may skip through because I've deliberately given you more notes than we can hopefully examine you on. I'll try not to waste time on things that we can do without this year. Okay? I hope they'll be there for reference for you. And then I want to move on, and it'll probably be in the 3rd hour, so I'm not going to use the last hour as a tutorial. But if we do go through chapters 3 and 4, those are actually tutorials 2 and 3. So I'd like to run through those and got solutions to those to give you today. So during the session that we're in here, we'll hopefully look at a couple of tutorial sheets as well. Okay? when we look at circuit elements, that's, if you like, one of the most complicated, and it's not complicated, but it is one of the most, the only bit of the maths associated with this module that I teach that's, I wouldn't say difficult, but if you cracked it, you'll have no trouble. And again, it's a very nice one to put as part of an exam question. So the third hour, I will be covering stuff which again is highly likely to be examined. Right. Like any good lab report, one of the first things you've got to include is a basic introduction and explain what the lab was all about. And those, I've written those down in the notes that I've given you. I've also put it on the lab notes themselves. So the sheets that you've just had, you'll see on page 2 suggested sections for your report, and I tell you a little bit about the introduction, the aims. If I haven't mentioned anything, that's because I don't want you to bother to about them. Okay? And you look at the marking scheme on the lab notes, and you'll see that we don't have to cover every section that would normally be part of a formal report. Okay. I think what we said, that hydraulics is a power transmission system. We've actually got a power pack which we use in the lab, and if we have a look at the lab itself, we've got that test rig, which is really a means of using that power. And we were actually driving this little hydraulic motor. And I was suggesting you compare the size of the hydraulic motor with the size of the electric motor. There was a little ram here, which I showed you, but which we didn't use. The whole test rig is extremely versatile, and the notes, if you like, or the handbook that came with it, is basically a good fluid power manual. So almost any aspect of fluid power you could actually demonstrate or experiment using that kit. Because we're looking at electrohydraulic systems, and I've asked you to look into fly-by-wire, it's fairly clear, I'm sure, as soon as you start looking at fly-by-wire, or you look at the specification of modern aircraft, both civil and military, that they rely entirely on computers. So the pilot is just one of the inputs into the system, and a lot of the inputs are feedback from transducers or encoders. We've got one on here, which is a rotary, we call it a tacho generator. It's effectively a little voltage generator. It's very precise, and the voltage it produces is proportional to the speed. Now, in the past, we have asked students to time how long this takes, say, for 50 or 100 reps, to work backwards and to try and confirm the constant for that one. But we were told that gives you 26 millivolts per radian per second. So basically, as long as we get the voltage that it generates, we know how fast the motor is turning. We know how much oil the motor takes for every revolution, so we can calculate the flow rate. And I said that's exactly what a petrol pump does. There is a pump down in the tank underneath, pumping up petrol or diesel out from that tank through what is effectively a hydraulic motor. And the output from that hydraulic motor is actually just clocking up the gallons, the litres, and the pounds for you. So the more it goes through, the more it turns. Okay? There's a nice trip hazard there. I've already clipped over the black one, so try the white one this time. Okay, so that's an essential bit. So if we had a fly-by-wire system where the output was a hydraulic motor, and if you look at an Airbus, for example, then the slats on the leading edge of the wing, the flaps on the trailing edge, are actually driven by hydraulic motors. They're actually buried in the fuselage, in the center wing box. And there are two hydraulic motors driving into what's called a differential. Now, you all know what a differential is. If you drive a car, there's one in the middle of each axle. Okay? probably know that if you were foolish enough to spin one of the wheels on your car, the one that's got traction stays still, and the one that hasn't just goes spinning. And it goes twice the speed of the mean. That's exactly the same. If we worked the other way around, if we jacked the car up and turned one wheel, it would probably try and turn the engine. If you jack both wheels up, turn one forward, the other one will actually go backwards. If we were to put a hydraulic motor to drive each of those wheels, they would drive the prop shaft, drive the engine. If instead of an engine, that was actually the gearbox that's pushing the flaps or the slats out, that's how we get two hydraulic motors. So there are two completely separate hydraulic motors. When both hydraulic circuits are fine, they both drive. So the output goes to both wings at the same speed. If for any reason you had to shut one of those circuits down, the hydraulic circuits, they put a brake on that shaft. The other one can carry on turning, and it will still drive the flaps or the slats out, but because we've now only got one motor, it goes at half the speed. They'll still go out. So that's typical, if you like, of the drive. We've got an encoder telling us how many revs the output has done. The computer knows that, knows how far the flaps and slats have gone out. If we, instead of using a rotary device, we used a RAM, a linear device, then we need an electrical signal. And this is a linear transducer. The obvious thing is to, and I have, oh no, yeah, here. If we look at electrical circuits, okay, so if we had a voltage on here, that may be say 12 volts, and this is earth, so that's no volts there. If we were to have what's called a rheostat, in other words, we slide a contact along there, if it's over at this end, it reads 0 volts. If it's over at this end, it reads 12 volts. And anywhere in between, it reads an intermediate voltage. You're happy with that? Basic ohms law. That's fine. So basically, if that was our linear transducer, the voltage that we would read on here would actually be proportional to where we move. The only thing is, when you've got a sliding contact, you're actually wearing away the electrical coil. So they don't generally like contact transducers. So what we've actually got in here is usually a magnet going to an induction coil. And you get the same thing, you get a voltage coming out proportional to where it is. Okay, there it is. So most transducers are non-contact, so they don't mechanically wear out. They usually fail some other way, like something on my car at the weekend. When your turbo goes on a diesel, it's absolutely gutless, isn't it? Except it's more economical. I've got a 2.2 litre diesel. We went down to Cheltenham on Saturday, 62.5 to the gallon. And just as we got there, the little warning light came out and it went gutless. So something has happened to the turbo or to the engine management system to sort of shut it down. Coming back, I know I had to go down to about third or fourth to get up some of the motorway gradients. 64.1 to the gallon. Can't be bad. Ford diesel engine in a Jag. Right. That's basically what we're doing. Hopefully you all identify the bits and pieces. I've asked you to identify the bits on the circuit. The notes give you the basic equation that Q, which is the flow rate, is some constant times the area of the hole through which the oil is passing, times, and what we've got there is the pressure drop, delta P, times 2, divided by the density of the fluid, to square root. So we're saying that basically the flow rate varies as the area through which the hole is passing. It also varies as the pressure drop. So we've got three different things: flow, area, and pressure drop. We can simplify that and take the density and the number 2, make it K2, a different constant, that gives us the basic equation that we were looking into. But if you've got three unknowns, Q, A, delta P, then you can't predict what will happen to two of them unless you know what's happening to the third one. So we looked at two different aspects in that experiment. In the first bit, we tried to keep the pressure drop going through the servo valve at 10 bar. Okay, so we were keeping that constant. We were controlling the area of the valve by applying a voltage to the servo valve. We assumed it's linear. And because the results look pretty good straight lines, I think that was quite a justified assumption. So you double the area, we double the voltage on it, the flow rate goes twice as much. And that's basically the first thing we were doing. We were trying to look at the quality of that valve, and I think because we all ended up with a pretty good straight line once you got the results the right way around, then that's fairly good. You can perhaps appreciate why they would use exactly that type of valve on a fly-by-wire aircraft system, because it is so predictable. We only did an experiment for one pressure drop, and you end up, and I want you to give me a result, as I have done on the bottom of page 3. 2 weeks ago we got 4.53. You may not get exactly the same, because it really just depends which points you draw the line through. You can adjust it a little bit. But you can see that we were fairly consistent between 4.5, 4.6, and it's litres per minute per volt, but only for this 10 bar pressure drop. Now 1 year we perhaps ought to ask a group of students to repeat it, trying to get the pressure drop at 5 bar, and then again at say 15 bar, and you'd end up with exactly the same sort of graph, but the gradient would be different. So basically you could then program the computer saying whatever the pressure drop is, and we've got this sort of lookup table, we can predict what voltage you need to give you a flow rate. So we were keeping that constant. In real life that would not be constant, but we can have transducers to tell us what the pressure drop is. The computer can then look at that pressure drop and say, if you want to open this to give me 5 litres a minute, you need to apply so much voltage. Okay? So that's really what we were looking at. Typical of what is the hardware, if you like, behind a fly-by-wire system, or many other applications. So that was fine. 3 variables, we controlled delta P in that one. Okay? Right. The other thing, which just to remind you, which I did earlier on, we used that hydraulic motor. Because we can assume that the oil is incompressible, it's not really, but it's not far off, then we can actually predict that for a certain number of revolutions of a motor, exactly we know how much oil has gone through it. Okay. So we've used that. When we go back and look at chapter 3, I want to talk about the efficiency a little bit more. So if in doubt, remind me. Then the next bit, we did that, we've done that. Yeah, the bottom bit, the 4.5, that's how big the motor is. The 26 millivolts we used, we didn't bother with those, but those are actually what we got. And then we got this servo valve. That's in chapter 4 of the notes on valves. I think anyone who doesn't understand what's happening, we'll go through that again when we look at chapter 4. Okay? Right. Get that. So typical results, that's what you've got, I suppose, isn't it? We were being very good at recording temperature, and once it had stabilized, it didn't seem to change very much. But temperature affects the viscosity of the oil. So when you're running an experiment, it's a good idea to make a note of almost everything that you can that could change or could affect the results. Because if the results don't come quite as predicted, in the discussion, you often want to find some reason or suggest some reason.
Give us a pencil.
When we look at that, we
That's
can
right.
fairly confidently say the temperature didn't change very much. We wouldn't expect the viscosity to have changed, so we don't expect anything strange to happen because of that. These were the two columns, and if you hover over this one here, for the voltage, sorry, if you hover over that, you can see the calculation that's embedded. I want you to check that, write it down in your results, and make sure you understand how we've calculated that flow rate. And it goes from about 6 litres a minute to -6 to +6 on most of the ones we've done. Okay, you got that. And then we recorded the pressures and worked out the logs. But of course, this is the log of the flow rate. So if those two columns had swapped round and this one has swapped with it, then that column's not right. The other thing which you can do is you can say, well, looking down here, that's a very, very low flow rate. That's because that's a very, very small voltage. So we know the motor's turning very slowly. Okay? You cannot get a log of 0. So anything close to 0 is giving us a number here which we're not very confident about. So when you come to plot log graphs, anything where that number is very small, you tend to be suspicious or willing to ignore it. So if you want to be careful or very pedantic, if you look, say, at page 5, I've pointed out to several points that I've ignored. If you hover over those points on your spreadsheet, it will tell you which row and column that you're actually highlighting. And you can then look and say, well, was it a very low flow rate? Is it therefore rather suspicious? Similarly, if you look at the graph that I put on page 3, just to the right of the 0, you'll find there is one point pretty well on the axis, and it's not on the straight line. Now, if you look at that particular one, I thought it might have included it on here, but I was looking at it, and it didn't quite tie up. And I suspect between somebody writing down the results and somebody else typing them into the computer, they probably read a 3 as a 5 or something like that. Now, I'm not saying you should fiddle the results. In this case, I left it as it was and ignored it. But I did change it, and it ended up straight on the straight line. So you can very often see that an obvious human error has occurred and come up with it like that. Okay, let's look at a few. This was the first week. And I deliberately changed the symbols and the colours. They're not very clear on the printouts that you've got. But you can see that here the blue ones are diamonds, and the purpley ones, they were supposed to be red, but they've come out as little stars. And the two groups, effectively, one group started over here with the motor going at maximum velocity in one direction. And we gradually reduced the voltage, and nothing happened to the flow rate, because that was the pump at full chat. And then it went straight down here, and then we ran out of pump flow, and it went off round there. Then the other group, the other set of symbols, started over here, and effectively did the reverse, and came back up there. There's the point that I'm a little bit suspicious of. Okay. Now, you've got to draw straight lines, and I've asked you to draw them manually. Let's just sort of see. That's the one, I think, that I printed. And I thought you weren't really being very naughty if you did one straight line through the whole lot, and you can work out what you think the gradients are. You can see that that and that are both 6 or -6 volts. Sorry, litres a minute. I came up with about 1.3 volts there, minus 1.35, which suggests that the whole thing is shifted over about 0.05. If I moved it half of that back, we'd probably find it went straight through the origin. Now, when you have a lookup table effectively of that sort of results, you correct for that, because we want 0 to be 0. In other words, if we put 0 volts on here, we don't want the valve to open. In this case, if you put 0 volts on, it suggests we're going to get a small flow in one direction. So you can correct that. What I did also suggest, though, was, that's the week 2 graph, unless you check your calculation, you'll probably find that one of those sort of stops about here and is all haywire. Right, let's go back. Those are the calculations that I've used, which are on there. If we go back to that first one, let's interpret it in a different way. I've exaggerated a little bit just to make a point. But you could perhaps suggest that this line and that line may be straight and may be parallel, but they don't actually join. Now, why would that happen? Effectively, we're putting a voltage on here to open the valve. What this is suggesting is that there's a band across here where the valve isn't actually open at all, or at least we're not getting any flow from it. It's only when I increase the voltage to this value here that this starts increasing, or I decrease it to there, it starts increasing there. Now you've all got a little cardboard valve. The little cardboard valve I gave you had an overlap in it. As you slid the spool backwards and forwards, the first little bit of movement didn't actually open the valve. So if the valve we had was like that, that's what we would get. In other words, we're saying that there's an overlap in the middle. You've deliberately got to move the valve a little bit before it starts controlling the flow. So that would be an honest interpretation if that's what the valve was like. But it's not. We're pretty sure that the valve is bang on, you know, you move it a little bit and it starts producing a flow. I think I told you that the hydraulic motor has got a little drain coming from it. The circuit diagram hopefully should show that. Because we don't want any leakage inside the motor to actually blow the shaft seal out. So we just bring it back to the reservoir. So it means because those little pistons, and it is a piston motor we've got, don't have any rubber seals on them, a little bit of oil can actually get past those. A little bit of oil is actually used by the slippers, I'll talk about those in a little while, to actually make them float like little hovercraft. So some of the oil that goes into the motor actually leaks and it doesn't turn. So what this could be suggesting is that up until we get there, we haven't got enough flow going into the motor to make it turn. And because this axis is the flow rate, if I extend it back there, that value there, or that value there, is actually the leakage. Okay? So we can read quite a bit into it. So we accept that it's a good valve that goes through the origin, but we're actually saying it's actually telling us how much leakage this will is giving. Now, I don't expect any of you to be convinced that the points you've got deserve that explanation, but that's an option. Here's another one. Two groups. One of you were going along the black line, the others along the red line. Now, when you come across graphs like that, we call it hysteresis. If you magnetize something, have you ever seen magnetic hysteresis curve? No. Well, effectively what's that saying is, when the voltage is decreasing, we get one set of results. But then we've got to increase the voltage a little bit before it will move in the other direction. Now that could be that the spool is sticky. In other words, you have to put a positive voltage to actually get it to move. So if we were here, you'd have to do a jump in the voltage before anything would happen, or the other way. Now again, look at your results, and you probably think, I'm going to have exaggerated that, which I have. But that might be another reason. So what I'm suggesting is when you look at your results, you don't necessarily have to draw one line and come up with one result. But I've given you sort of a few explanations as to what the valve might be doing and what actually might happen. Let's just go back to this one. Yeah. I think I suggested with this one that this valve, if it had an overlap on it, would give us something like that. If you're trying to control an airplane by fly-by-wire, the last thing you want is for the pilot to move the stick a little bit and for nothing to happen, which is really what would happen here, or the next one with that hysteresis. So actually the valves that are used generally have not an overlap, but an underlap. They're always a little bit open to both sides. Now that sounds very dangerous, if you like, but it's not, because you completely eliminate that problem. It means that the valve is always slightly in between the two, and as soon as you move it a little bit, it has a slight effect, one way or the other. It actually means that over this little bit, you actually get a steeper bit of a graph. So you get more precise control around the neutral, and then once you start going quickly, you're not quite so worried. But that very delicate control that you want around the mean position is actually improved by having an underlapped valve. Okay? Now, we're getting into the realms of more sophisticated hydraulics than you'll need to deal with. But really, that's why this experiment is actually so appropriate, that there's an awful lot in it that links into what happens in the real world. Okay, so that was the first bit. And I think once you've sorted out the equations, etc., you've got some very good results. There are one or two points that you can say, well, somebody must misread that or mistyped it or something. But that's why you draw graphs. And that's ideally why you draw graphs as you go along, so you can backtrack and try again. Right, same equation. We also measured the return pressure just before it went through a restrictor. So we actually had a restrictor and we kept its area constant. We could have adjusted it, but once we'd set it, we left it as it was. So we're really saying that the flow through a hole should be proportional to the square root of the pressure drop. That's what Mr. Bernoulli says. I think from my results, it doesn't agree with that. Instead of getting an answer of a 0.5 or square root, we were getting an answer of about 0.9. I don't know, you can probably make yours a little bit better by ignoring some other points. Okay. What we got? There we are, so that's what we've done. And the trick was we took logs. So we plotted a graph of log Q against log delta P, and the gradient n should be the answer we want, which gives us an answer. And that's the same as the equation of a straight line. So it's a very common trick in maths and experimental work to actually take logs to linearize a function. Okay. Again, if we have a look at the graphs, this was group 1. We've obviously got some there. The red and the blue again for the two halves of the group. That's the results I got from those. I've chosen to ignore those. But what we would really like would be for this to be smaller and that to be bigger. In other words, give me a graph which was sloping less. So if I sort of looked at that one and said, well, perhaps I should have pushed this line to go through that point and down through this point, that would have actually given me a gradient of about 0.75, 0.8, which is getting a little bit better. And it's the same results as just how we interpret them. Okay? So we may want to look carefully at why we're ignoring some of these points and make some excuses, if you like. I've given you some because, A, log of 0 is meaningless, log of a very small number is very predictable, things like that. Okay, the group last week, when we got the results correct, came up with that. That's my straight line through there. There was obviously one point right down here, which I ignored. I think the pity with the Excel is if there's a point down here, it sort of shrinks the rest of the graph to include it. If you just take that line out, it expands the graph, so you might choose to do that. Okay, is there anything of the lab then that you are not happy about? Because I'm afraid I'm not going to see you before you hand it in now. If you've got any serious queries, drop me an email. But hopefully with those notes, read them quite carefully, because I have explained most of those things in the notes. See how you go.
With the the circuit that we've got to draw for the fly-by-wire.
Yes.
I'm struggling with that. Is it? I don't know if anyone else is.
I am.
Yeah. Can't find anything on it, like.
Yeah. We would do that next time. Which isn't much help because you'll have done it by then, or you should have done it. Right, can we see this board?
Yeah.
Yeah. I'm just asking you to look at one little bit of a circuit. So let's just okay. Let's assume we've got a ram rather than a hydraulic motor. If we're thinking of the ailerons, let's just say, take the ailerons if you want. So the actuator for the ailerons would probably be a double-acting ram. So there's our piston. But we would have a rod sticking out of each end so that we get the same area. On this direction we've got an area like that. On this side here we've got an area like that. And because we've got a hole in the middle of both of them, we've got the same areas. Which means if we put the same flow rate in, it will move at the same speed, up or down. If we put the same pressure difference in, it will give us the same force. So the forces are to do with the air going over the aileron. The more we have to push against it, the higher the force. That will predict. So that's our actuator. What are we going to have? We're going to have a pump. Right. There's the hydraulic pump. Now, do you want to drive it off the engine? Do you want to drive it off the electric motor? Doesn't matter, does it? If we were driving it off the engine, we would do that. Okay? That's the engine. If we did that, that's an electric motor. Now, Airbus, sorry I keep going back to Airbus. I think I told you, 10 years ago I got seconded to Airbus, so I've become a bit of a fan ever since. It also means that I've got lots of friends in Airbus and I can get a little bit more information out of them. If you look at the A380, it's all the Airbus aircraft since the A310 have been fly-by-wire. Okay, so they've all used hydraulic circuits, rather like that, to control most of the hydraulics. On the A380, because it's the most recent aircraft to be flying, things are improving. A, they push the pressures up, so they're working at 5,000 psi, 350 bar. But electric motors are now getting much, much smaller. And they've also got such big wings that they would like to distribute circuits around the aircraft. So actually on the ailerons, they've actually got three completely different control systems. They've got a traditional fly-by-wire, where they've got power coming off one of the engines. They've actually got little power packs that are part of the actuator. So out on the wing, they've got a complete circuit. Okay? So I think we will assume a complete circuit. Let's try and change these the other way around. So that's an engine, but the electric motor so we've got electric motor. So we're now actually thinking of a little power pack where we've got a little electric motor driving a pump, controlling a ram, all pretty well next to each other. The ram is going to be controlled by a valve because we need to be able to have three positions